Okay, so now we are in the module that is on linear algebra. Our first topic is vector spaces, matrices, and linear systems. Okay, so if we can define a vector space. If you remember, a vector space has 8 specific, I think it's 8 or 10 properties. Definition. Okay, a vector space V is a set of vectors going to call them V1, V2, all the way up to Vn. All right, with operations plus and times. So now if you remember, there are certain properties of vector spaces. The vector space has to be commutative, has to be associative. That's an addition and multiplication. It has to be an identity element for the addition. The identity element for multiplication generally is 1. It has to also, every element has to have an inverse, an additive inverse, and it has to be distributive properties for over addition and over multiplication. And also multiplication by a scalar constant also puts it back into the vector space. All right, so that's the vector space there. Because vector spaces don't necessarily contain vectors, they can be polynomials, they can be 4x4 matrices, they can be, I'm not going to put the vector sign over top of the vectors. So just we know that that's a vector space. So an example, so here's some examples. You guys know vector spaces very well. Okay, the first one I want to give you is V is equal to vector space Rn. We like that one. That one does every element in Rn. V is a vector, and the vector has x1, x2, all the way up to xn elements. And it also has addition and multiplication, and also is a vector space over some scalar field. Okay. And then 2, we also have the vector space could be the set of all polynomials of degree n. So therefore, a vector inside of that vector space would be something like P0 plus P1 plus all the way up to, no, that's wrong. P1x is what I want to write, plus P2 x squared, all the way up to Pn xn. Okay, so everything there and all the PIs are all real numbers. Okay. All right, so that's 2 different vector spaces that we know of. All right. We talk about linear combination. So let me see, let me go back over here, underline this definition. Yes, okay, I want to underline this next definition. Underline. Okay, so here we now say let V, all right, be a vector space. All right, and let V1, V2, all the way up to Vn be elements of V. Okay, then the vector V equal to alpha 1 V1 plus alpha 2 V2 plus ... plus alpha n Vn is what? What is that? What's that called? Oh boy, y'all there? What's it called? What's it called?
Linear,
You're right. Linear combination. Okay. Where alpha I is also, they're all real numbers. So that's a linear combination of the vectors in V. Okay, another definition. Ooh, boy, oh boy. I think I'm pulling all the stops out now. Come on. This is my thing, linear algebra here. All right, so let's let V be a vector space. All right, and let I'm gonna do this set Vi, I equal 1 to n. That set, those be an element of V. So that set, that whole set, no, I can't do it like that. That would have to be contained in V. I'm gonna have to do them separately. V1, V2, all the way up to Vn, be elements of V. Okay. Then the whole set is linearly independent. If there exists, if whenever alpha 1 V1 plus alpha 2 V2 plus all the way down alpha n Vn is equal to 0, then alpha I is equal to 0 for all I. So anytime you have a linear combination of the vectors in V and you set it equal to 0 and all the alpha i's have to be 0, then it's linearly independent. Okay, if there exists one or more, I should say at least one, if there exists at least one alpha k not equal to 0, then this set Vi, I equal 1 to n is linearly dependent. Okay. Definition. The set Vn is a basis for V if A, the set Vi. So what's the requirement for it to be a basis? The set has to be linearly independent. And for all alpha in V, there exists a set of alpha 1, alpha 2, all the way up to alpha n, such that you can write V as a linear combination of those, i.e., the set. What's the word I want, guys? What does it do? What does it do? A pleasant four-letter word. Spans V. Okay. Theorem. Crash course in linear algebra. If V is a vector space, with basis Vi, I equal 1 to n, then every basis for V has n elements. That is, the dimension of V is equal to n. Okay. All right. Crash course, crash course, crash course. All right. One vector. My notes need some organization. Okay. Set 1, x squared, x cubed, x to the 4th, x to the 5th, x to the 6th is a basis for P6. The dimension of P6 is 7. Okay. And then 2, I hope you remember these. E1, E2, these really are vectors. E3 up to En is a basis for Rn. Okay. And I think I'm going to go back to Rn over here, and I'm actually going to make this transpose only because I like it better when the vector is vertical. So I'm going to go back and put a little transpose on that. And then my E's are going to be in Rn. And so EI is the vector 0, 0, 1, 0, 0. And this is the ith row. Okay. All righty. Okay, that's vectors. Let's go on to matrices and linear systems. Okay. So let's talk about an M by M. So here we have a matrix M. I'm not really good with making M's. I just don't do well. Okay. Here we go. M, and this is M by N. All right. Turns out to be the set of all matrices A11, A12, A13, A1N, A21, A22, A23, all the way up to A2N. And then we go all the way down to AM1, AM2, and we're going to go all the way over to AMN. All right, such that Aij is a real number, or it could be complex, but we're just going to stick with real number for now. Okay, so that is a vector space. That vector space is the vector space of all M by N matrices. Okay, so again, in a vector space, this vector space, multiplication is not commutative. Let's just remember that. All right. And if M is equal to M, then they're all the square matrices of order N. Okay, let's talk about some matrix operations. I think you guys might remember these. Okay, so we're going to let A and B have order. We're just gonna make them an element of m by n. All right, and we're going to let alpha be a real number. So the first thing is the matrix C is equal to A plus B. So we can add these, is also an element of m by n, and we can say each Cij is simply each Aij plus Bij. So we can add them component wise. Okay, number 2. We can talk about the matrix C that equals alpha times the matrix A. This is also in m by n. And here Cij is simply equal to alpha times Aij. Okay. And we can talk about the matrix C equal to A transpose. All right, this is an element of m, n by m. All right, it is not an element of m by n. It is an element of matrices n by m. And here all the Cij's are equal to Aji. So we're just going to do them in a separate order. Okay, if we have C is equal to A star, this is now also an element of m, n by m, and these are the conjugate transposes. So Cij is equal to Aji, but if this thing is complex, these are conjugate transposes. And we call A star, it's called the adjoint of A. And I have one more I think I can squeeze in this last minute. And that is, let A be an element of m by n. And now we're going to let B be an element of m n by p. And so now we can talk about C being the product of A times B. And this thing is an element of m by p. And each Cij is equal to the sum k equal 1 to n of Aik Bkj. Okay, and I will stop there. If you are rusty on linear algebra, I suggest you take some time